All right, segment 6 of chapter 6, Energy and Chemical Change. So we've been working our way through all of the different components of heat, energy. We finished off with delta H of reactions, delta H's of compounds, and now we're going to look at delta H in reactions. So enthalpy changes in chemical reactions. Of course, we'll be focusing on the systems. So it's going to be endothermic. Then that means we have, do you remember, reactants, products, and our heat is where? Very good with the reactants under endothermic. And of course with exothermic then the heat will be part of the products. All right. So want a convenient way to use enthalpies to calculate reaction enthalpies. So what we want is a way to just tabulate the different energies for a given reaction. So whenever we have a given reaction, if we set up those reactions in standards, then we know that that heat will always be a constant. And so then whenever we look at a reaction, we can say the enthalpy for that reaction is X under these conditions. So we simply just need a way to tabulate those enthalpies, and the way we're going to do that is with what's called the standard state. So this is going to specify all the necessary parameters to describe our system. It generally includes pressure, temperature, and the amount and state of the substances involved. So the standard states in thermochemistry then, number one, the pressure will always be 1 atmosphere. The temperature will be 25 degrees C, or preferably 298 Kelvin. The amounts that we'll use will always be 1 mole. All right, so formation reactions and phase transitions. So we're always going to be looking at moles. And then the amount of substances equals moles in an equation. So obviously if I'm going to balance the equation, we're going to set it to be 1 mole of one thing. But the other things could be the multiples based on that small number ratio, that small whole number ratio, which we call the coefficients. All right. Thermodynamic quantities, E and H, are state functions and are also extensive properties. Right? So extensive versus intensive, do you remember that? Delta E and delta H are measurable changes, but still are considered extensive. Right? Often used where N is not standard or specified. Now N is the number of moles. So delta E prime and delta H prime, or not, we like to say delta E sub naught, delta E naught and delta H naught are standard changes and are intensive properties. So units of kJ per mole for formation reactions and phase changes, which is why we're going to use the naught or the prime. Okay, so what that's telling us is that's going to be per mole. That's going to take away that dependency in there. It's going to make them intensive properties. The units of kilojoules for balanced chemical reactions. Okay, so we're going to be in kilojoules per mole for formation reactions and phase changes. So there's two types of reactions here we're looking at, right? We have formation, so we're going to make something, and then phase changes, so solid ice going to liquid water. Units of kJ for balanced chemical equations. And notice the subs here. So delta H of formation is a sub F. Delta H of vaporization, right? So that'd be like the vaporization of water. So we're going to go from liquid water to steam. And then versus of reaction, right? So delta H of reaction. All right, so standard conditions, again, are 25 degrees C, 1 atmosphere, 1 mole. So the standard heat of reaction then would be the enthalpy change for reaction at 1 atmosphere and 25 degrees C. So here's a formation equation. We have nitrogen gas plus hydrogen gas forming ammonia gas. And of course, we can see it's 1 mole to 3 moles to produce 2 moles. When N2 and H2 react to form an H3 at 25 degrees C and 1 atmosphere, 92.38 kilojoules is released. So delta H should be what? Positive or negative? Now remember, if it's needed for the reaction to take place, then it would be a positive, and that means it's going to be a reactant. If you're producing that heat, then that means it's going to be a product and it's going to be negative. And in this case, it says it's going to release 92.38 kilojoules, which means delta H then will be a negative 92.38. All right, that leads us to thermochemical equations. So what we'll do is we're going to write delta H immediately after the equation. So the next time you're in lab, if you look up the CRC book over there, it's over in the safety area of our lab. In that book is tabulated all of these different reactions. And so what it'll look like is this. It'll be N2 gas plus 3H2 gas goes to 2NH3 gas. Delta H is equal to negative 92.38 kilojoules. Now, obviously, that means per mole of nitrogen, right? Per mole of nitrogen. Now, you must give physical states of products and reactants. Okay, that's because delta H will be different for different states. So for instance, if I take methane gas and I react it with oxygen gas to form CO2 and liquid water, then it's going to be negative 890.5 kilojoules. If we produce gaseous water, then it's only going to be 802.3 kilojoules. And that's because it's going to take us 88 kilojoules to vaporize the water. Okay, so some of that heat goes into the state change from liquid to gas. All right, write the delta H immediately after the equation. It's also going to assume the coefficient is the number of moles. So that means that 92.38 kilojoules releases when 2 moles of ammonia are formed. If 10 moles of ammonia formed, well then it's going to be 10 for an H3, 15 H2, 5 N2, and we're going to multiply the 92.38 by 5, and that's going to be negative 461.9. Okay. Now, you can also have fractional coefficients. Now, it's fraction of mole, though, not fraction of molecule. So obviously, you're going to have more than 1 mole, right? Or more than 1 molecule, rather. So half of N2 plus 3 halves of H2 will give us 1 NH3. So if I wanted to eliminate that 2, then I could just divide everything through by 2. And that's how we got there. And of course, if I'm dividing these by 2, I'm simply going to divide the delta H by 2. And so that's going to give us negative 46.19 kilojoules. Now again, you really have to be paying attention to the states here. When you're looking up those values, it can be a little bit confusing to make sure that you're in the right state. So state is going to matter. So here's propane gas reacting with oxygen to give CO2 and gaseous water. And here it is with liquid water. Now, note there is a difference in energy because the states do not match. Okay, that's the big difference in it. Now, if water liquid going to water gas, that delta H is going to be equal to 44 kilojoules per mole. Therefore, if the difference is going to be 4 waters, then it should be 176 kilojoules per mole. So if I take the negative 2219, I add the 176 that it cost me to make the water turn to gas, then you can see the difference there is going to be negative 2043. Okay. All right, so let's consider acetylene. I'm going to burn our torches here. That's going to give us negative 2511 kilojoules. The reactants, acetylene and oxygen, have 2511 kilojoules more energy than the products. How many kilojoules are released for 1 mole of C2H2? So again, hit pause here, you maybe jot down some notes. Well, to get this, all we're going to do is take what it would cost for the reaction and divide by how many moles are in the reaction. In this case, 2 moles of acetylene. Moles of acetylene will cancel out, and so we'll get negative 1256 kilojoules. All right. Given this equation below, how many kilojoules are required for 44 grams of CO2 to react with water? So if I take 6 CO2s plus 6 waters, I'm going to make 1 solid sugar and 6 oxygens in gas. The delta H for that reaction is 2816. Notice it's a positive value, right? Given the equation below, how many kilojoules are going to be required for 44 grams of CO2 to react with water? So I'm going to start with 44 grams of CO2. I'm going to get the molar mass from the periodic table, get that into moles. That sounds familiar, like we've been doing that for the last 5 chapters. Then I'm going to look at what it's going to cost me per 6 moles of CO2. So now I can see my grams of CO2 will cancel out, my moles of CO2 will cancel out, and now I'll just run that through my calculator to get 470 kilojoules. So it's going to cost us 470 kilojoules of energy to make that reaction go. Now, if 100 kilojoules are provided, what mass of CO2 can be converted to glucose? So now I'm going to start with that 100 kilojoules and work backwards, right? So I'm going to go to the 6 moles of CO2, and then I'm going to do 44 grams over 1 mole. And of course, later we're going to see how we deal with gases, and that can be that third piece. Okay, but for right now, we've done masses and we've done molarities. So kilojoules cancel out, moles cancel out, and 9.4 grams. All right, so based on the reaction for methane to react with 4 chlorines to make carbon tetrachloride and HCl gas, the delta H for this reaction is negative 434 kilojoules per mole of methane. What energy change occurs when 1.2 moles of methane reacts? Here are your options. That was your pause. So if you need to pause, you can do it now. And hopefully you came up with E, negative 5.2 times 10 to the 2. All right, so delta H is going to equal to negative 434 kilojoules per mole times 1.2 moles. Moles cancels out, and we get 520.8 kilojoules, or 5.2 times 10 to the 2 kilojoules. All right. Reaction 1, propane gas mixing with oxygen gas, forming CO2 gas and water as a gas, negative 2043. If the water is a liquid, then it's 2219. Why does reaction 2 release more heat than reaction 1? Give you a few moments here to read those. So pause it if you need to. And hopefully you said in reaction 1, some of the heat of the reaction is used to convert liquid water to gas, so less heat can be given off. Okay. All right. The next thing we're going to look at then is reversing thermochemical reactions. So we've already said that if I take methane, I mix it with water to make gaseous, or excuse me, mix it with oxygen to produce gaseous water, that's going to be negative 802.3. What happens when I reverse this equation? So in other words, I'm going to take the products, turn them into reactants, turn the reactants, and turn them into products. So here we're going to have CO2 gas plus 2 waters is going to produce the methane and the 2O2. Notice what happened to the sign of the delta H. It went from negative 802.3 to positive 802.3. So whenever we reverse the thermochemical equation, it simply changes the sign. Okay, so reversing thermochemical equations changes the sign of delta H. Hopefully that makes sense, right? If you get energy out when forming products, then you must put energy back in order to make reactants. The consequence of the law of conservation of energy, right? Just like a mathematical equation. If you know delta H for reaction, you also know delta H for the reverse reaction. The other thing we want to look at with delta H is multiple paths. Can often get from reactants to products by several different paths. So in other words, the reactants could go directly to products, but in reality, reactants probably go to some sort of intermediate A, which then goes to some sort of intermediate B, which then goes to products. And maybe you have several other intermediates in the middle here. It doesn't matter. What matters is that you understand that there's 2 particular paths that we can do here. That means no matter which path that the reaction takes, we should get the same delta H naught. So enthalpy is a state function. Remember, it's path independent. All right, so let's take a look and see if we can figure out if this is true or not. So multiple paths, same delta H. Path A, single step. Carbon solid plus O2 gas goes to CO2. The delta H for that reaction is negative 393.5 kilojoules. Now, path B is going to be 2 steps. We're going to take carbon, we're going to mix it with half of an oxygen to produce CO. Then we're going to take that CO and add another half of an oxygen and get CO2. The delta H for the first reaction is negative 110. The delta H for the second reaction is negative 283. If I sum these up, right, then remember before how we were doing ionic compounds, things would cancel out. That's what I'm going to do here. I have C plus a half of an oxygen and a half of an oxygen gives me a whole oxygen. I have CO on this side and I have CO on that side. They're going to cancel out, and so my product's going to be CO2. Since I just simply added up all of the pieces of the reaction, I'm going to do the same thing with delta H. So negative 110 plus negative 283 gives me negative 393. Chemically and thermodynamically, we get identical results. Now, this is going to be true for both exothermic and endothermic reactions. All you have to do is sum up the delta H's, and everything should work out to be the same. All right, so path A, N2 plus 2O2 goes to 2NO2. That's going to cost us 68 kilojoules. Path B gives me N2 plus O2 going to 2NO. Then I'm going to take those 2 NO, add some more O2, and get to 2 NO2. Now, the original step 1 here took 180 kilojoules of energy to do, but the second step gave us 112 energy back. Again, we'll sum these up the same way. So I'm going to take N2 plus 2 O2s. The 2 NOs will cancel out. I'll get the 2 NO2 as a product. Then I'll simply sum up 180 plus a negative 112, and that gives me positive 68. All right. Hess's law of heat summation. For any reaction that can be written in 2 steps, the value of delta H reaction for the reactions will equal the sum of the delta H reaction value of each individual step. So one of the things we do to help us out with this is we look at what's called an energy diagram, or an enthalpy diagram. In this case, we'll be looking at just the enthalpies. So obviously energy delta H is going to be on your y-axis here. So down here will be our base value, up here will be the maximum. And you can see if whether we do it in steps or whether we do it in a single step, the values should be the same. So basically all this is just a graphical description of Hess's law. The vertical axis is our enthalpy, the horizontal is simply telling you the various states of the reactions. The higher up you go, the larger the enthalpy, the lower down you go, the smaller the enthalpy. And again, we can do this for any set of reactions, okay? A lot of times you'll see these whenever we're trying to measure delta H. So in other words, we can look at reactions that we can't actually recreate in the lab by looking at enthalpy diagrams. So arrow down delta H reaction means negative. Arrow up means that it's positive. Okay. So we can then calculate based on the cycle. So 1-step process, the sum of the 2 steps. So in other words, to go from here to here would be negative 286. To go from here to peroxide would be negative 188. We can then calculate the difference of that second step. Okay, so an example here, we have peroxide going to water plus 1/2 O2. Okay, so we can go from here to here, and we can look up what that value is by taking the negative 286, which was the whole process. We know that's going to equal the negative 188 plus the reaction we're looking for. Okay, so we'll take the negative 286, we'll subtract the negative 188, that gives us negative 98 kilojoules. So this piece here should be 98 kilojoules. All right, so that would be the reason for using the enthalpy diagrams. What is your change in altitude if you climb up a 7,005-foot mountain, drive a car from that spot down 2,003 feet, then parachute down another 11,500 feet into a canyon? Draw a diagram that reflects your changes and your calculation. Okay, so here are your options. Maybe pause here, quickly do some scribbling. Hopefully you realize you went actually 6,500 feet lower than where you started from. So you had your starting point. You were at, say, what is your change in altitude if you climb up? So it doesn't tell us what we started at, it just says you were here and you climbed 7,005 feet. From the 7,005 feet, you then drove down the mountain a little bit, 2,003 feet. At that point, you were at 5,002 feet. Then you harnessed up in a parachute and jumped. And you went 11,508 feet into the valley, which puts us at negative 6,506 feet from where we actually started. So your change in altitude was actually negative 6,506 feet. Okay. Now again, the change is negative because the altitude decreased from your final state being lower than your initial state. All right. So we're going to end here. We'll do probably what's going to be maybe our last segment coming up for Hess's law, where we're going to take advantage of these summations.